Hello, welcome to another module in this massive open online course. So, in this module, let us look at another interesting application of linear algebra in the context of machine learning. This is basically termed as Eigenfaces. Alright. So, let us look at another application. This is essentially, you can think of this as an extension of PCA to face recognition. So, this is a very popular and a very significant algorithm. This is an application in the context of, as I already told you, machine learning, right, or essentially what is abbreviated as ML, and this is basically, you can think of this as extension of PCA for face recognition applications. So, this is an application specifically in the context of face recognition. This is termed as Eigenfaces. And what do we mean by this Eigenfaces? What is the procedure for this Eigenfaces algorithm? Let us consider a typical face image. For instance, one can say a typical, I am drawing a caricature here, a typical face image comprises of pixels. You can think of this as basically comprising of, so this is the image of my cartoon image of a face, and this comprises of essentially each of these is a pixel. So, this is basically a face image a frontal face image, and let us say there are MC rows of pixels. Let us say there are MC rows of pixels. And there are MC columns, and there are MR rows of pixels in this facial image. Okay. So, you have in the face image MC equal to number of columns of pixels, MR equal to number of rows of pixels, and therefore, total number of pixels, this is given as MC times MR. MC into MR, let us call this as M. M is the total number of pixels. All right. So, now each image xi, each image, now you see each image can be represented by the matrix which contains the pixel values. All right. So, each image can be represented by the matrix. So, the ith image can be represented by a matrix, all right, xi. This is essentially the ith image. This contains of size, as I told you, MR cross MC. This will be of size MR, where MR is the number of rows, MC is the number of columns, MR cross MC. So, each image Xi is essentially a matrix, right. So, an image is essentially a two-dimensional signal which contains certain number of rows, certain number of columns, which contain basically the pixel values, right. So, let us say these columns are Xi1, Xi2, XIMC. These are the columns, right. So, this is the ith image XI. This is a matrix of pixel values. This is MR cross MC, and it must be clear, but let me write it. This is the matrix. An image is a matrix of pixel values. Okay. And if you look at this, these are the columns, right. Columns of pixel values, there are MC column, size of each column MR cross 1. So, each column in this is basically of size MR cross 1. So, if you look at an image, what we are saying is, let us take a simple example. Let us say we have a 256 cross 256 image, which basically has 256 rows and 256 columns. It's essentially a matrix of size 256 cross 256. It has 256 rows and 256 columns of basically pixel values. So, you can arrange this as a matrix comprising of 256 columns. Each column has 256 elements, all right. The reason we are doing is because now we want to form a vector. So, from this Xi, which is the ith phase, which corresponds to basically ith phase in, you can think of this as your training data set. Ith phase or ith phase in your set, right, ith phase in image set. Let us think of it that way, ith phase in the image set. So, you can now from Xi obtain vector x tilde I by stacking, obtain x tilde I by stacking the columns. That is, we have x tilde I, you stack the columns of Xi one below the other. So, you have Xi1, Xi2, stack the columns one below the other or one above the other. You have MC columns, each is of size M cross 1. So, you are basically stacking the columns, right. So, this would also be fairly easy to understand. This is a standard operation. This is also known as the Vec operation. So, what you are saying is Xi tilde in mathematics, this is also known as the Vec operation, right. So, you take a matrix and stack its columns to obtain a vector, all right. And naturally, this x tilde I is going to be, it contains basically you have MC columns each of size M. So, this is going to be MC into MR cross 1 vector, but MC into MR equal to 1. So, this is going to be MR cross 1 and this is going to be a vector of essentially, all remember that this is going to be your vector of this is going to be the vector of pixel values. This is going to be the vector of pixel values. Okay. And consider now n images. Consider now and so we are going to be, so we are obtaining this vector from the image, which is essentially a matrix of pixel values. We are obtaining this vector of pixel values, and now we are going to illustrate the procedure for face recognition. So now let us say you have m images in your face set, okay, your face image set or facial image set. So you have x1, x2 up to xm, and corresponding to these, so these are the face images, right. So these are your facial images. And corresponding to these you have x1 or x tilde 1, x tilde 2, so on, and x tilde m, which are the corresponding vectors. And then now what we do is, how the question we want to ask is, given a new image, a new face, given or given an image, given a facial image, given a facial image x, right, given a facial image, new facial image x tilde, how to recognize this? That is essentially how to map it to your existing set. That is, which face does this correspond to? Does it correspond to x1, x2? Which one of the existing faces does this correspond to? Alright, so you have an existing, a vast database. So let us think you have this database of faces, right, and now you have a new face. Let us say this belongs to some person you want to identify. Now to which facial image in your database does this new face correspond to? And you can see that clearly this has a lot of applications, a lot of, whenever you want to identify some person, you want to identify an unknown person from an image of his or her face, you would call upon this algorithm. So, and this has vast applications you can imagine, right. So, this is your, you can think of this as essentially your database, alright, your database of facial images. Now, the Eigenfaces algorithm proceeds as follows. Remember, we are talking specifically about the Eigenfaces algorithm. So, we will talk about the procedure for the Eigenfaces. So, we will talk about the procedure for Eigenfaces is as follows. So, what we do is similar to PCA. I hope all of you remember the principal component analysis algorithm that we have described before. You form the mean vector of these facial images. So, you have this 1 over n, I am sorry, this should be n, this is the size of your database, right. So, you have 1 over n summation I equal to 1 to n xi tilde, this is the mean. You can also remember this is also called as the sample mean and from all the images subtract the sample mean. So, you obtain from each image xi, you obtain x bar I equal to x tilde I minus mu bar. So, we subtract the sample mean So, we subtract the sample mean and then we form the covariance matrix. Now, form the covariance matrix. We form the covariance matrix, or rather the estimate of the covariance matrix, which is given as R equal to 1 over n minus 1 summation I equal to 1 to n xi bar Hermitian. So, this is basically your covariance, this is basically your covariance matrix, right. So, this is essentially your covariance matrix. Now, once you form the covariance matrix, we form the eigenvalue decomposition of the covariance matrix, and that is given as V. You remember the eigenvalue decomposition, that is given as V lambda V transpose. Remember, this is an eigenfaces algorithm, right. So, there is some relation to the eigenvalues and eigenvectors. In fact, that is what we are going to see. The eigenfaces algorithm, as the name implies, has a very deep relation to the eigenvalues and eigenfaces. What is the relation? This is the relation. So, we talk about the eigenvalues of this covariance So, this is basically they are the covariance matrix, and this is basically the eigenvalue decomposition. We have the covariance matrix, this is basically the eigenvalue decomposition, and from this essentially what we do is we find the eigenvectors largest principal. So, we find the eigenvectors, remember similar to PCA, find eigenvectors V1 bar, V2 bar, Vp bar, these correspond to the largest principal components. Okay. Or you can think of this as the directions corresponding to the largest principal components. Alright, you find basically these are the eigenvalues corresponding to the p largest eigenvector, or these are the eigenvectors corresponding to the p largest eigenvalues, alright, of the covariance matrix. These are eigenvectors corresponding to p largest eigenvalues. P largest eigenvalues of R, which is the eigenvectors corresponding to the p largest eigenvalues of R, which is basically your covariance matrix. Okay. And now what we do is we form the principal component vector. Alright. So, for each image, x bar I, form the principal component vector. Form the principal component vector, and we know this is given basically by taking the projection of each facial image x bar I along the principal directions, along the directions of the principal components, right. So, essentially what we do is now we have the W bar I, which is basically given as you take the projection of V1 bar, this is your V1 bar transpose, V2 bar transpose, Vp bar transpose times your x bar I. Okay. So, or essentially we are saying this is your Vt transpose x bar I and this is your W bar I, and this will be a p cross 1 vector, alright, and these are the principal components corresponding to image, principal components for, you can think of this principal components for the face I, principal components for the ith face. These are the principal components for corresponding to face I, and remember this matrix V is V equals again V1 bar, V2 bar, Vp bar, which you can clearly see each vector is the size of M. So, this will be M cross P matrix, alright. And now, so this is basically your, you can call this as the weight vector for image I, weight vector of face I. This is the weight vector for face, this is the weight vector for face I. So, you can see this is also basically nothing but a representation of face I, a compact, a compressed p dimensional representation. Remember that is what PCA gives us. What PCA does is it determines the principal components corresponding to the projections of each facial of each data vector along the directions which have the largest variance, right. So, this is a vector containing the p, you can think of it as the vector containing the principal components of the face I, or the significant components, or the largest, or the components of the face I that has the largest variance. This is a compressed version of that, rather than storing that and using that large dimensional, that m dimensional vector. Remember each face image, if you think about it, 256 cross 256 image of pixels, right. So, if you represent that as a vector, that will be 256 times 256, which is essentially 2 to the power of 16, right. So, that is a large vector. We are taking the significant directions or the significant components of that along the eigenvectors of the covariance matrix corresponding to the largest eigenvalues, calling that as principal components, and this is basically compressed representation of that facial image, alright. And now we similarly form, so now we similarly form from your x1 bar, x2 bar for these images in your data set, we form the weight vectors, right. We form the weight vectors W1 bar, W2 bar, W2 bar. These are the weight vectors corresponding to the images, facial images in the database. Weight vectors for facial images in the, these are the weight vectors for the facial images in the database. And now how to perform the facial, so these are the weight vectors for the n images, right. In your database you have n images, and now what is the procedure for how do we perform facial recognition? As we said, let x tilde I be the new face that is not yet identified, x tilde I be the given face image. Corresponding to x tilde I, we subtract the mean. Now from x tilde I we obtain x bar I by or x bar, from x tilde we obtain x bar as x tilde minus mu bar, that is we subtract the mean. Once again, now find the weight vector corresponding to x bar, this unknown, the face of this unknown person. Now find the weight vector. Weight vector corresponding to x bar, that will be given as w bar, which is v transpose times x bar. So, you are finding the principal components corresponding to x bar, and this is the weight vector for the unknown face, alright. So, this is the weight vector for the unknown face. This is the weight vector corresponding to the unknown face, and now compare this with the weight vectors of the images, right. Compare this with the weight vectors of the images in your database. Compare this w bar n, correct, w bar n for images in the database. Alright, and the face image, from the database with the closest weight vector to w bar is the recognized image. Essentially that is the idea. So, you compare it. So, you form the distance di of the weight vector of this unknown face to each vector in the, so this is the distance, right, this is the L2 norm, which is essentially the distance, or you can think of this as the Euclidean distance. This is your essentially or distance metric, or this is essentially the distance of the weight vector w bar I from weight of each image I in the database, and then find the least, find the image I, find the face image I with the least distance. Find face I with least distance implies find I tilde equals argmin, which is essentially the minimum argument of di, that is the distance di, the I such that the distance di is minimum, and I tilde, this is essentially your recognized face. This I tilde which basically corresponds to the minimum distance, that is a weight vector which has the minimum distance, weight vector I, w bar I, which has the minimum distance to the weight vector w bar of this new facial image, that is essentially the recognized image. So, this is your Eigenfaces algorithm for face recognition. So, this is essentially basically your, the whole thing that we described so far is basically what we call as the Eigenfaces. Eigenfaces algorithm. This is basically the Eigenfaces algorithm for face recognition. The only small change here is going to be the fact that see, sometimes this image, this new image of a new face, and practical practice that might also arise frequently, that is this facial image of this unidentified person might not actually be present in your database, right. So, it might not correspond to any facial image in your database. So, typically we compare this distance with a threshold. So, di, so compare di or this di tilde rather, that is the minimum distance that you found, di tilde with some threshold epsilon. If this minimum distance di tilde is greater than epsilon, then it essentially means that that minimum distance, that is no face in the database, is a close match, alright. Then it does not match with any of the facial images in the data set, alright. So, this typically means that this implies that the unknown face this implies that the unknown image does not correspond to any face image in existing database. In existing database, alright, it does not correspond to any unknown base because it is not particularly close to any of the images in the database. On the other hand, if this di tilde is less than equal to epsilon, else if di tilde is less than epsilon, then this matches to face I tilde, then it matches to face I tilde, alright. So, this match. So, essentially what you do at this point is you announce face I tilde from the data set as the closest facial image, that this unknown image, you announce face I tilde. Essentially you announce that I tilde, it matches to that face I tilde, or essentially what you can do is, instead of taking the, in fact there can be variations of this, instead of taking the facial, if you have a large database, sometimes what might happen is that it might closely match with the images of several faces. So, you might not just take the I tilde which has the least distance, but you might take a certain number, let us say 3 or 4, or a certain number k of images which have the lowest distance corresponding to the weight vector of this new unidentified face. And then you do a manual search, or you probably do a more an expert search, right. You call in an expert or something of that sort, and then try to better identify or more carefully identify which of these faces in the database does this face correspond to, or does it not in fact correspond to any face at all. So, these are all variations of this algorithm. So, the essential idea here is that you are taking this large database which potentially comprises of a large number of facial images, and moreover each facial image itself we considered a modest resolution of 256 cross 256. These high resolution facial images nowadays, because of the improvement in the resolution of the cameras, these can be 512 cross 512 or 1024 cross 1024 and so on, which means the size of each vector can be huge. So, you have a large database of faces, each data point has a huge size, and now how do you take a new facial image and essentially announce, compare it, or essentially check with which facial image in your data set this new facial image matches, or which the image in your data set to which this new image corresponds. Alright. So, this is the Eigenfaces algorithm which can be used, which is essentially a machine learning application of the principles of eigenvalues and eigenvectors that we have learned so far. It is an interesting application of, and essentially PCA, right, principal component analysis, essentially a very interesting application of, I would say, linear algebra and PCA in a practical context of practical example of facial recognition. All right. So, with this, let us stop here and we will continue with other such interesting applications as well as new concepts in the subsequent modules. Thank you very much.